All right, my favorite demonstration of Faraday's law is the so-called jumping ring. It's the principle behind electromagnetic launchers, which have been proposed for space travel from the moon. But really, we just have a solenoid, remember, that produces a uniform field inside, and that field kind of branches out a little outside of it. And if I turn on that field, it will try to change the field through something up here. And by Faraday's law, we expect a voltage to be induced, and if there's a continuous path, a current. Now, it so happens this is an alternating current, so I'm turning it off and on many times when I turn it. So I'm going to put another loop on it, just a series of coils connected to a light bulb, so that as we change the flux through that loop, we'll induce a voltage and the light will light. And it's an alternating current, so this will happen many times per second. Okay, so that's the principle, say, behind a transformer, to have one coil producing a flux and a second coil receiving that flux. And if it's a continuous path, then it can support a current. So let's look at the same thing for a simple mechanical demonstration. Here's a ring. I'm going to put it on there. And remember the key feature. When you try and change the flux through something, a current is induced that opposes that change and thus opposes that current producing that change. So if you have opposite currents, they will repel. So let's see if this loop is repelled as we turn on that field. I'm going to step on this foot switch. Ready? Go. Nothing happens. So why? It's because this loop is not continuous. If you look closely, it has a gap in it. And that gap means that even though we induce a voltage around it, no current can flow. And if there's no current flowing, nothing can cause a force to oppose that other current. But if we take instead a continuous loop, here's a piece of aluminum that does not have any gaps, so now currents can flow. Let's go ahead and turn that on and see what happens. Watch it carefully. Okay, that was pretty good. We got some good height on that one. Let's try it one more time. If we maybe put it under this light, we can see it a little better. Go. So we almost reached the light. We can do a little better. Remember, we learned something a few weeks ago about electrical conduction, that in metals, if you decrease their temperature, they become better conductors. If the resistance is lower, that voltage will cause a larger induced current. So I'm going to cool this cylinder with liquid nitrogen. Liquid nitrogen boils at 77 Kelvin, about negative 196 C. It's not toxic, it's what we're breathing. 80% of the air is nitrogen. But it's a good way to get things cold. You can see it boiling away here as some of it vaporizes in the cooling of this ring. All right, I think it's fairly cold. It's certainly a lot colder than it was. Let's take a look at what happens if we try to induce a current in this ring. I'll drop it on and ready, set, go. All right, we got the ceiling. All right, so we need a continuous path and a good conductor to get something traveling quickly.